Hi, welcome to my video. In this video, I am showing some examples for vector space. In my previous video also, I have given the examples for vector space on continuation. Here I am going to give another example. Let us go into the video. Show that the set of all ordered n tuples of the elements of any field F is a vector space. So what is we need to prove is that set of all ordered n tuples of the elements of any field F, that F has scalars, is a vector space. So here the solution goes as such. Let F be a field and n be a positive integer. Let Vn of F be the set of all ordered n tuples of the elements of the field F. That is Vn of we described as, so when I say Vn of is suffix n, okay, there are n components. So each element will be of this form, x1, x2, etc. up to xn, where xi belongs to F. So if you take any elements from Vn of F, it has n components and that will represent in this form x1, x2, xn, and this is only is called ordered n tuples. Also the two elements alpha and beta, when it will be equal in the sense, you know that any element comes from alpha, it should be in this form x1, x2 up to xn, and beta should be of another element y1, y2, yn. When alpha is equal to beta means x1 must be equal to y1 and x2 must be equal to y2 and xn is equal to yn. So when I say 1, x2, y2 all, I am representing only the suffix. Now, before going to prove that it's a vector space, let us define addition and scalar multiplication as below. So, how to add any two elements, and using the scalar multiplication, how to multiply, we'll define as such. Alpha plus beta is equal to x1 plus y1, x2 plus y2, etc. x1 plus y1. That is component wise addition. Each component we have to add. So, and then similarly C dot alpha, Cx1, Cx2, Cxn, etc. is a scalar. So, each component we need to multiply with C, where C belongs to F, hence Vn of is closed with respect to scalar multiplication. Now, we need to prove that Vn of is a vector space using these two compositions. So the very first one, we need to show that Vn of is an abelian group. For abelian group, already the addition is closed. From the definition only we can understand. So the next property is going to be associative law. So I have taken three tuples, that is x1, x2, xn, 1, and another element y1, y2, y1, and z1, z2, zn. And let me add y1, y2, yn plus z1, z2, zn. So when I add this, I can combine as y1 plus z1, y2 plus z2, etc., yn plus zn. And adding this, we will be getting x1 plus y1 plus, it's a component wise addition. That is what already we have defined, how to add any two elements which belongs to Vn of F. So component wise, when I add, I will be getting that x1 plus y1 plus z1, x2 plus y2 plus z2, etc. x1 plus y1 plus z1. So this I can split it as all in addition. So this we can take it as combining x1 plus y1 together and plus z1. Here x2 plus y2 plus z together, and here's etc. x1 plus y1 plus zn. Now this again we can write it as x1 plus y1, x2 plus y2, x1 plus yn, and then this is with z1, z2, zn. All these are possible due to the definition which we have already defined. And then this I can split this as x1 plus y1. We can write it as x1, x2, xn plus y1, y2, yn plus zn, z2, zn. So it is a plus b plus c is equal to a plus b plus c. So that is what it's being given. So the associative law is we can able to prove that it's satisfied. And then next is going to be existence of identity in Vn. So let us see what is the identity element in Vn. So we have 0, 0, 0, etc. is also a element which belongs to Vn because it has 0 components, n components. We can always express that. And then if I take another element x1, x2, etc., xn belongs to Vn, then if I add x1, x2, xn with 0, 0, x1 plus 0, x2 plus 0, xn plus 0, that is nothing but x1, x2, etc., xn. So from this we are able to prove that 0, 0, etc. 0 is the additive identity in Vn. And now next I should find out additive inverse of each element of En. So for that, since x1, x2, etc., xn belongs to En, then obviously minus x1, minus x2, minus xn is also a Vn because all are scalars. Also we can write this as, if I add minus x1 minus x2 etc minus x1 with x1 x2 etc xn by adding minus x1 plus x1 minus x2 plus x2 etc minus xn plus xn, so that will give 0 0 etc 0, which belongs to Vn. That means minus x1 minus x2 minus xn is the additive inverse of given element x1 x2 etc xn, which also belongs to Vnf. So and the last one is going to be commutative law. So commutative law, you take any two tuples, so that is x1 x2 etc x1 plus y1 y2 etc yn, then adding s1 plus y1 x2 plus y2 xn plus yn. That is, we can write it as yn plus x1, y2 plus x2, etc. yn plus xn, because addition is always, the either way 4 plus 3, 3 plus 4, it gives 7 only. So same thing, principle only are applying here. So I can, instead of writing xn plus y1, I can write it as y1 plus x1 and y2 plus x2, etc. yn plus xn. Then again I can split this as y1, y2, etc. yn plus x1, x2, etc. xn. So from this, a plus b is equal to b plus a. So commutative law is also satisfied. Hence, Vn is an abelian group under addition, with respect to addition. Now we need to prove that if the remaining axioms. So if alpha is equal to x1, x2, etc. xn and beta is equal to y1, y2, etc. yn be any two elements of Vnf, and C dash belongs to F. That is, C is one scalar and C dash is also another scalar. Now we prove the remaining axioms as the first one is going to be C into alpha plus beta. So I should prove that C into alpha plus beta is equal to C alpha plus C beta. So C into alpha plus beta is, what is C into alpha plus beta? C into alpha we know x1, y1, x1, x2, etc. xn, and beta is y1, y2, etc. yn. Alpha plus beta means it is x1 plus y1, x2 plus y2, xn plus y1. So this is, you have to multiply with a scalar C. So each component we multiply. So that will become C into x1 plus y1, C into x2 plus y2, etc. C into xn plus y1. And this again we can say scalar again, since we can write this as cx1 plus cy1, cx2 plus cy2, etc. cxn plus cy1. Now again this is an addition, I can split it like this: cx1, cx2, etc. cx1 plus cy1, cy2, etc. cy1. Now this all that's a scalar. C is common, I can take it out, C outside. So C into x1, x2, etc. xn plus C into y1, y2, etc. yn. So this is nothing but alpha and this is nothing but beta. So C into alpha plus beta is equal to C alpha plus C beta. The second one is going to be C plus C dash of alpha is equal to. So what is C plus C dash of alpha? This is a scalar. C dash is also scalar. So C plus C dash into alpha, x1, x2, etc. xn. So this is a scalar. I'm just multiplying with that. C plus C dash x1. So C plus C dash x2, etc. C plus C dash xn. Then again we can split the C to cx1 plus C dash x1. Cx2 plus C dash x2, Cxn plus C dash of xn. Then this we can split it as Cx1, Cx2, etc. Cx1, and this plus C dash x1, C dash x2, etc. C dash xn. So again C we can take it out from the, as C is common. So C into x1, x2, xn, and here it is C dash, we can take it out from this. So C dash into x1, x2, etc. xn. So it is going to be C alpha plus C dash alpha. So C plus C dash of alpha is equal to C alpha plus C dash alpha. All this you have to remember the definition which we have defined in the beginning, and the same way only we are proceeding here. And the third one is going to be C into C dash of alpha. So C into C dash of alpha means C dash alpha is x1, etc. x2. So it will become C dash x1, C dash x2, etc. C dash of x1. So multiplying with that, we will be getting C dash x1, C dash x2, etc. C dash xn. So taking out C dash is a common in all the components. So C dash I can take it out. So C dash of x1, x2, etc. xn. So this is nothing but our alpha. So the third axiom is going to be C into C dash of alpha is equal to C dash of alpha. So the last one is going to be 1 into alpha must be equal to alpha. So let us check what is 1 into alpha. So 1 into alpha means it is 1 into alpha is x1, x2, etc. up to xn. So 1 into x1, 1 into x2, 1 into xn. So that will become x1, x2, etc. xn. So that is nothing but alpha. So 1 into alpha is also equal to alpha. Always remember 1 is going to be the unit element in the field F. and now it satisfies all the axioms. You have proved it obeys the abelian group conditions, also the rest of the axioms, and hence Vn of is satisfy all the axioms of the vector space. Therefore, Vn of is a vector space over the field F. So Vn of, in the sense it has a set of ordered n tuples, is a vector space over the field F. Thanks for watching. Please like and subscribe for more videos.